Hey everyone, we're gonna get started. Can the people on Zoom hear me, or just the one person on Zoom? A thumbs up.
That's good.
All right, I'm hoping this person can hear me. Anyway, hey everyone, welcome to our first in-person workshop in the last 2 years. We're gonna be talking about optimizing machine learning code in NumPy and SciPy. So before we get started, there are some to-dos on here. Join the Slido. So if you go to slido.com and enter that code, we'll have some questions and stuff over the course of the workshop. That's a good way to ask questions as well. If you don't want to raise your hand, it's easy to post an anonymous question there. The slideshow, the notebook, and also an associated blog post are all there as well. If you just go to the slideshow link, you can get all the links for the rest of the presentation. And obviously the required plug, if you're not a part of Data Science Club, you should join and sign up and check out all of our YouTube channel and stuff like that. This workshop will be posted on YouTube later, so you can check it out afterward. Cool. And with that, we'll get started. So welcome to the workshop. This is on behalf of the U Waterloo Data Science Club. You guys all probably know about the Data Science Club, but we're an academic club that basically focuses on teaching students about data science, getting people involved, and connecting like-minded students. And so it's a great thing to be a part of, and keep coming to our events. And it's presented by me, Nick. My contact information is right there. If you have any questions, please feel free to reach out. Happy to chat about this workshop or about whatever. So just a quick overview of what we'll be talking about. Kind of the key motivation for this workshop is that whenever you're implementing some kind of numerical algorithm, whether it's ML, whether it's scientific computing, whatever it may be, you really got to implement it efficiently, especially with the amount of data that we have today. And I think what you guys may have experienced is that it's really easy to write super slow code in NumPy and SciPy. Even though they claim to be super fast libraries, if you kind of misuse them and don't write code in the right way, it's going to be pretty slow. For this workshop, I kind of expect that you guys have some beginner level NumPy SciPy knowledge. Really, this just means that you imported it once and used an array a couple of times. I don't really expect too much, but I do want you guys to be familiar with the kind of overall goals and how to use it on a high level. And in terms of SciPy, to be honest, if you've used NumPy, that's enough. You don't really have to know SciPy too much. I also expect a little bit of machine learning data science knowledge in terms of the Kmeans algorithm. I'll do a quick overview and kind of ask you guys how much you already know, but this workshop will be smoother if you do know it, and if you don't know it, it's not a big deal. And kind of the high level goals are, we're going to talk about 3 techniques in particular: broadcasting, vectorization, and sparsity. And if we have time, we can go into other stuff, but I doubt we'll have time. So this is our first Slido thing. So if you try the Slido, there's a QR code there, and there's a number here as well. Give me a rating on a scale of 1 to 5 on how familiar you are with NumPy. So 1 means you've never used it or imported it once, and 5 means you've been using it every day for 2 years. So let's hopefully this live thing works. Sweet, it works. Cool, I guess that's about everyone. Okay, a 2.6 on average. Okay, everyone's kind of used it a little bit. That's kind of what I expected. A lot of people in the 1 category. I'll try to explain things a little bit more, but might be a little rough. I'm not gonna lie. We'll see how it goes. So the next thing is, how familiar are you with K-means? So this is really just to calibrate how long I should spend on introducing the algorithm. 5 means you know it pretty well, you kind of understand it, and a 1 means you've never heard of it ever in your life. Okay, not bad. Oh, I think my audio, is it working? Yeah, I think it's working. Okay, hopefully it's working. Anyway, cool. So thanks for that. That'll help calibrate my explanations a little bit as we go on in this presentation. And so here's a quick outline of what we'll be covering today. The first thing is basically a high level of what NumPy and SciPy are. Even though I kind of expected you guys to know a little bit, we're going to go over it again. We'll do a K-means in 5 minutes, basically going over an intuitive overview of how K-means works. And it's basically going to be the focus of our case study today. We're going to be optimizing the implementation of this algorithm and seeing how we can go from something pretty simple to something still simple, but pretty fast. And the bulk of this presentation will be on the actual implementation, as the name kind of implies. We'll first focus on an initial implementation, something that you might write up pretty quickly off the back of your, just off the cuff. And then we'll work on optimizing the 2 main steps within the K-means algorithm. So the first one being the assignment step, and the second one being the update step. And with that, we'll just wrap up, and that should be the workshop for today. How do I get rid of this top bar? Get rid of this. Oh, I have a chat here. Okay, cool, nice. Okay, so before we talk about why we're using NumPy or SciPy, we should first talk about why not just use normal Python. Like Python has built-in lists, we can do math in Python. Why don't we just keep doing everything in Python? So pure Python can be pretty slow when you kind of scale up to very large problems for a couple of main reasons. The first thing is that it's interpreted and not compiled. And so what this means is that every action that happens in Python is dynamic. There's no preset instructions for the CPU to run. Every step is kind of queried in an interpreter and run dynamically. And so I know that's not a very descriptive answer, but the focus of this workshop is not that in particular, but just know that interpreted languages tend to be slower than compiled ones. The second and slightly bigger problem is that it's single-threaded. And so Python has something called a global interpreter lock. And this basically means that only one procedure can be run at any given time. Whereas if you think of other programming languages, you can have some sort of parallelism where multiple things are happening at once. And this is kind of a problem for numeric computing because a lot of the time we have problems like matrix multiplies or just normal addition with vectors where you can kind of like parallelize that. That's not possible in normal Python. And kind of the final problem is there's many indirections. If you kind of think of a list of lists in Python, that's not just one chunk of memory, right? That's like a list and a pointer to many other lists. And so basically your program spends a lot of time looking for where the information is in your memory, as opposed to actually manipulating and doing operations on the memory itself. And so this illustration here, if you can see my mouse, yes, you can, is basically like an example of a Python list of lists, right? If you think about a language like C or C++, it'd just be like a continuous chunk of numbers that you can manipulate. But here you kind of have a list and that points to a new set of lists that points to the actual numbers themselves. So that kind of leads us into why NumPy and SciPy. And so basically NumPy provides really efficient multidimensional arrays. You don't have this problem of like a lot of indirections, everything's contiguous in memory. You don't have like this interpreted language, everything's compiled and fast written in either C or Fortran, which is super great. And SciPy is kind of the analog to NumPy in the sense that instead of providing this like data structure, it provides many efficient algorithms as well as other data structures. And so for scientific computing, whether it be signal processing, machine learning, etc. So kind of as I mentioned before, unlike Python, it's compiled, which is great. It can take advantage of all the cores on your computer. It's like multi-threaded and it can do, for example, like a matrix multiply and parallel. It uses your memory more efficiently. I mentioned before, you kind of have a chunk of memory to work with numbers as opposed to many indirections, and this tends to be more efficient. There's like really optimized implementations because people have been working on this for years and years and years. It's standardized in the community, like all these libraries are built on top. There's just a lot of reasons to use NumPy and SciPy. Oh. So before we kind of get into it, we can think about some like high-level rules about how to like write fast NumPy. And kind of the number one rule that I'm going to be focusing on for the rest of this presentation is avoid using for loops and instead use some kind of vectorization. And we'll kind of go into more detail about what that looks like. And the rest of this stuff is kind of, it's kind of a secondary consideration for the rest of our presentation. It's like understand the memory model, create a more efficient algorithm, fewer function calls, like that doesn't, these are all kind of small fries. The really big one is the vectorization aspect. So I said a lot of things about kind of introducing Python, NumPy, and SciPy. Do you guys have any questions? Feel free to raise your hand or pop it in the Q&A in Slido. Cool. Oh, and I guess the number one rule, I forgot I had a little thing popping up, is even though we have like some high-level rules for writing fast code, the number one thing is to benchmark. Whenever you're working with anything that has to do with performance, you may have some intuition about what happens, but that intuition is often wrong because of how complex our modern machines are. So you should really time things, experiment, see what works faster. And obviously, don't spend all your time optimizing, just optimize to the point where it's sufficient for your task. So I'm going to have a quick conversation about how memory is kind of managed in NumPy. This won't be too important for the rest of the presentation, but it'll help you think about some of the things that we'll talk about later. And I thought these were going to be animated, but I'm using Slido's presentation thing right now, and apparently they don't really support the bullets coming in one at a time, but it's not a big deal. So pretend we have a NumPy. So even though these look like lists, we're going to pretend they are actually NumPy arrays. This is like the representation when you print them. Let's say we have this array. This array has like 8 elements, 10, 20, 30, all the way up to 80. And this is like a contiguous chunk of numbers in memory. The cool thing about NumPy is when you reshape these arrays, a lot of the time you're not making a copy of that data. You're instead just interpreting the same data in a different way. So in particular, for the second line here, I want to say, okay, reshape this array to something that has 4 rows and 2 columns. And you see here that we have the brackets around that represent like a matrix of those dimensions. But actually underneath the hood, this doesn't make a copy at all. This is just interpreting the same continuous eight numbers as a different shape. So what does this mean for us? So obviously, 8 elements on an array, like you can copy that no problem. But when you have something super large, like maybe millions of elements in an array and you want to reshape them, a lot of the time you're not copying that. And so you're not using extra memory. You're not taking the time to allocate a new array. And so a lot of these operations are very fast. And same thing if you want to, for example, look at every other element. So this is called a stride in NumPy. And so this notation, if you guys are familiar with NumPy, is like taking every other element of the array. And so here, the same thing is happening. There's no new array being created. Instead, it's just looking at the array and saying, okay, we're going to skip every other element, but just interpret that same chunk of data as something different. As final example is the exact same thing. We're doing a transpose here of the 4x2 matrix and getting like a 2x4 matrix. And again, once again, no memory is moved. It's just interpreting the same data in a different way. This is kind of an important concept of knowing when NumPy is going to take a copy versus when it's going to just interpret the same data in a different way, because it can be the difference between running out of memory and being able to do something. So this is just kind of a brief overview. We're not going to go into the memory model anymore. The only thing I want you guys to remember is a lot of the time you don't make a copy, which is great. We'll see why that's important later in the presentation, but just something to keep in mind. And I'll have links later for you to read more about why this happens. Any questions about things I've said so far or any of this? Yep.
What is the syntax for the stride?
Okay, yeah, good question. So basically, normally when you, for example, if you want to do a slice of an array, let's see if I can actually do this in real life. Can you see this? So cool. Okay, so we can have an array of 8 elements here, for example. Let me do times 10. So normally if you want to take a slice, for example, like the second element to the 5th element or whatever it may be, you can do that. And so that's like the first number represents the start index. The second number represents the end index exclusive. And so, for example, 5, R5 is actually 60, but 1 to 5, it's exclusive. And then when you have another colon, then you include a number. This tells you the stride, so what the step is between the elements. And so here we would expect 20 and 40, right? And so 20 and 40, it's like taking the steps over. And so, for example, if we instead take the original array, if we exclude the first 2 numbers, they're implied to be the start and the end. So it's this is the same as doing 0, and this is the same as doing the length of the array. Does that kind of make sense? And then so right here, we can do stride 2, and it kind of steps over every other element there. Sound good? Cool. Any other questions? Nice. Okay, yeah, well, I had a question slide, so you guys can ask questions. Can someone ask a test question? I want to see it pop up here. Nice. Okay, cool. Yes, this is what we're using for the rest of the presentation. It's my first time with Slido, but this is pretty nice. All right, cool. So the next portion of our presentation will be talking about k-means in 5 minutes. And so the algorithm we'll be optimizing is k-means. And I kind of expect, at least most of you to kind of know what it is, or we'll go over how it works. And so we all have a good understanding before we get into the meat of the presentation. So what is k-means? You might have heard the term, it's an unsupervised clustering algorithm. And honestly, those 3 words together don't really mean too much to the average person. And so let me just explain it with somewhat of an anecdote. And to pretend you're a smartphone maker, let's say you're Apple. Actually, no, Apple would never do this. Let's say you're Samsung, who wants to decide what size phones to make. And so you survey your customers and say, okay, what is your preferred height and width for a phone? And so you can imagine the size being some kind of vector, right? It's like a 2-dimensional vector of height and width. And so basically they want to decide what the best 3 sizes will be based on the closest fit to the most people. They want to make the most people happy. And so they want to basically decide on 3 sizes that kind of minimizes some error between what people prefer and what their actual phone size is. So if you take this collected data and you do k-means on it with a k equals 3, essentially it'll identify 3 clusters in the data of preferred phone sizes. And k-means will return kind of the centroid of each of those clusters, which is essentially the closest fit to the 3 sizes that customers would most prefer. This will make more sense when I illustrate in the future slides. And so just on a high level, how this works is if you have some data set, so this is a bunch of vectors. So for example, the size that people prefer, and you have the number of clusters that you want to find in the data. So from the previous example, that was 3. And so the goal is you want to assign each of those points to one of the k clusters and kind of find the centroid of each of those clusters. So the high-level process is as follows. You kind of choose 3 random points at random in your data, and these are like your initial centroids. You basically look for what the closest centroid is, the closest centroid is for each data point. And so by close, I'm talking about Euclidean distance. And so like, the square root of the squared distance, basically. The next thing is you now have these like groups and clusters of points that kind of belong to one group, and you want to update the centroids by finding the average of each of these groups. And so basically you kind of repeat between this assignment step and this update step until you finally come out with your final groups when the centroids no longer change. And so how does this actually work? So let's go through an example. So you can see here on the left-hand side, we have, let's say we started out with a bunch of random points, and then these like circles with the holes in the middle, they're like the initial centroids. So we have 3 initial centroids here. And so now you can see that these points are kind of assigned to their closest centroid based on Euclidean distance. So for example, all these purple points are assigned to this purple circle, these 2 red points assigned to this one, and all the blue points assigned to this one here. In the next step, what you want to do is recalculate what these centroids should be. So for example, here, this little circle here is like the center, like the average of all these points. This one's the average of all the blue points, and this one's the average of all the red points. Does that make sense? Any questions about that? Great. And now we're just going to repeat this process. And so here, this is the previous step from the previous slide already, like that first iteration. And then now we basically reassign the points. And so as you can see, we have some more like these points over here were kind of assigned to this centroid because they're actually closer. We have a few points over here that's assigned to this centroid over here. And so they're basically reassigned to the closest centroid. And then we recompute the centers, right? Like these are slightly off center, and then they're kind of recomputed to the middle of their cloud of points. We can basically go through these steps a couple times until finally we have these like distinct clusters of points and their centroids that it's closest to. So now we have these like 3 clusters from our data. Does that kind of make sense on a high level? Is what we're going to be working on? Cool, great. Okay, though this is a question type. Why not use C++ for speed? Let me how can I archive this question? Nice. Okay, good question. So C++ tends to be like, if you haven't worked with C++ before, it tends to be very verbose and not as expressive as something like Python. And obviously, for algorithms that really need the down to the metal speed, C++ is what's really common in the industry. Like if you're an engineer working on high performance numerical algorithms, you're probably in C++. But if you're more of a scientist, like a data scientist or some kind of researcher, and you don't really need the performance down to the metal, and instead you're, something like NumPy is sufficient, where you have a high-level API and pretty good performance, that's usually a good middle ground because you tend to be more productive in a language that's like high level. You don't have to worry about, strict typing, appeasing the compiler, et cetera, et cetera. So your sense just to be a trade-off between the performance you can get and versus like how fast you can iterate. I hope that answered your question. Feel free to post a follow-up if that didn't. Any other questions, especially about the K-means that we just talked about? Cool. So this is going to be our like initial naive implementation. And don't worry, after I go through this, I'll give you guys a chance to actually play with the code, which I have posted up here. But let's just go through what this does exactly. And so just to start, we have our like K-means function, and essentially we're taking the data, which is basically like an array. It has n rows and like d columns. So it's like an n by d matrix. So where n is the number of like data points in our data set, and d is like the dimension. So for example, in our smartphone example, d would be 2 because we have like 2 dimensions, the height and the width. The first thing we do is we choose some random points in our data to be our centroids. And so we can do that through numpy.randomChoice. And so basically we're saying, okay, we have n different things. We want to choose k of them. And so this will return k different indices that are unique. And so this will give us like k unique centroids. And so for example, in our smartphone example, k was 3. We want 3 different unique centroids. And the last thing we're doing just for setup is we have some labels that we're going to use later. Don't worry about this for now until I explain the next step. This is just going to be an array. Eventually, it's going to assign each data point to a centroid. So this is going to have numbers ranging from 0, 1, and 2, because we're 0 indexing for the 3 centroids. In terms of like a performance standpoint, this preamble doesn't really matter, right? At the end of the day, most of the work is going to happen when we kind of iterate over the data multiple times, because we're going to be doing this, like, this setup is going to happen once. The iteration is going to happen 50 plus times, right? 50 is just a default I have here. So these steps we can kind of ignore for the sake of performance, at least for now. The next thing is a slight difference in our algorithm versus what I just explained. So previously I said that, okay, we're going to keep doing this process until our centroids don't change. But when we're kind of measuring performance, that's going to be a little bit annoying. We're going to have like a variable number of iterations, and like we're going to have to check the stop condition. Just to simplify this presentation, we're going to have a fixed number of iterations. And so, for example, we're going to repeat steps 2 and 3 like 50 times or something like that. And this is something pretty common in libraries. You'll find that they have like a convergence condition, and they also have like a maximum number of iterations. There's cases where the algorithm can, like, for example, not converge, but we won't talk about that. Oh, I should probably stop actually. Any questions about this kind of setup, like what we have here? Oh, and by the way, I have in the comments like the shape of the arrays that we're getting. And so, for example, the centroids are like k different centroids of dimension d. So like 3 by 2, for example. Any questions? Check Slido. Oh, cool. Now this is like step 2 from our algorithm in the previous slides. It's the assignment step. And so here we're basically determining which, like for each point, which centroid is the closest point to that centroid. And so we're just going to do this with a simple for loop first. We're going to go through all the points in the data. And next we're going to calculate the distance. So the norm calculates the Euclidean distance between this point and every centroid. And so we have k different centroids. This will give us a list of length k. And the next step, we're going to basically determine which one of these centroids is actually the closest. And so we have k different distances here. And by taking the argument, we're determining, okay, which centroid is the closest. So for example, if the 0th centroid is the closest, argument is going to return 0. And our labels array will be populated with a bunch of indices from 0, 1, or 2. And basically in the final step, this is kind of the update step where we update the average centroids as we iterate through. So this is a little bit more complicated here. So basically, for those who have used NumPy, you know that this syntax is called Boolean indexing. So basically, we're taking this expression is going to be false wherever the label isn't equal to I. So for example, if we're on the first iteration where the label isn't 0, and we're basically taking all the data points that belong to that particular label. So for example, centroid 0, the first iteration would take all the data points that belong to centroid 0. Then we're going to take an average of those data points. So once we have all the points that belong to centroid 0, we take a mean, and we are left with just one vector of dimension d. That's like the average of all these points. And obviously, we're going to do this for each of the k different centroids and labels. And finally, even though before I told you that we're going to assign the points to the actual centroids, here we can just return the centroids, and the user can do the next assignment step themselves if they really need to. So I know there's a lot of information. I'm just going to do one more thing, and then we're going to actually play with this implementation a little bit before we continue with the presentation. And the thing I'm going to do is basically, here I had a comment determining the assignment step and the update step. Here we're just going to turn those into functions. And basically, we're going to call the assignment step, get out some labels, determine and call the update step, and get out some centroids. And so just for some initial timings, we can make some random data. To kind of motivate these numbers, I've chosen 5,000, 26, and 26. 5,000 is kind of arbitrary. Your data set can be as large as you want it to be. 5,000 is just a good number for us to work with kind of locally here. K being 26 is somewhat of a reasonable number, right? Like you don't want too many clusters when you're doing k-means. Often it's in the single or double digits, and 26 is pretty reasonable. And it also shows like performance characteristics because it'll be more easy to tell different algorithms apart when it's a little bit larger. In terms of d, the dimension, we know that k-means doesn't work too well. Your dimension is way too large. We're going to keep it on the same order of magnitude as k and just make it 26 as well. And so this algorithm, when I ran it on my computer, it took like almost a minute to run 50 iterations here. And so that's kind of our baseline starting point. So now what we're going to do is we're going to take maybe like 5 or 7 minutes, just go to the notebook, and the first little block will have the actual code. And I know like my explanation was a little bit quick in terms of each of these sections. And so I'd like you to like kind of look at the functions, look at the code. I have some inputs and outputs there. Just take a look and see what's going on so we have a better idea before we go forward. And yeah, 7 minutes. See you guys.
They should hear my voice when she's on the slides. Slide up. Should be very similar to the
Sure. Oh, really? Oh, hold on. Let me look at it. Oh, difference between K and D. Yeah, good question. So K is the number of clusters you want in the end. So in our smartphone example, like you want 3 different clusters of phones, right? A small, medium, and a large phone. So K would equal 3 there. So it's the number of clusters. D is the size of each of your vectors in your data set. So in our smartphone example, we wanted to get the height and the width of each phone, right? So that's 2 dimensions, and so D equals 2 there. And so that's kind of the difference between K and D. Feel free to add a follow-up if that didn't make sense. Okay, also, yeah, so while you guys are kind of playing with this code, if you want to like update it and modify it and try to make it faster, you can like, I think you should see a thing on Slido where you can kind of say how fast your code's running. There's like a time it thing there. And so, yeah, post how fast your thing is going. So for example, like the baseline assignment, it goes like 700 milliseconds. And so, yeah.
share away.
Yeah.
So let's say here data fix 2026 labels. Oh, wait. I think
Oh, okay. So we have a bunch of numbers. So let's say like labels. So how many things are so how many of these centroids are actually assigned? So it will be 0 and then we'll do like how many so this so basically this will be true wherever it is. So remember the first so if we do like that, right? We can see that's going to be like 0 to 1. So that means some and say we see that 216 of these rights are kind of belong to centroid 0. So in these labels, is that going to make sense? Cool. So when we actually do this like so we take this like the true false we have right here data and then the actual shape. You see that we have 216 different data points and they're all okay. Yeah, exactly. And then when you do the mean 0, so that's as well. So if you like the so I consider all the tiles for 0. So now we have a single vector of the average of all yeah. And so basically when you stack those up, when I do the stack, so first you like have the mean of the 0th centroid. The second one is like the mean of the first centroid. Does that make sense? Yeah. Okay. Yeah. Okay. Yeah. Continue our question. Yeah. Okay, so we have another good question here. What's the meaning of time its output? That's a great question. So basically, it's time it basically runs your code multiple times and then basically gives you an average. It does multiple trials. Okay, so it loops your code multiple times and it also does multiple trials of these loops. And it takes like the average of each loop and then finds the best of the averages. That was a super bad answer because I actually don't know the precise method it works underneath. But just think of it as running your code multiple times and kind of taking the best average time. That was super unsatisfactory, but just it's a good average as opposed to like if you just ran it once, there'd be a lot of variance and so instead like time it gives you an actual spread instead of just a single number. Good question. I should have known a more detailed answer to that though. Feel free to ask follow-ups if you haven't. Okay, cool. I think we'll continue and get going unless anyone has any questions or comments before we leave or to the next thing, I mean. Cool. Actually, okay, let me take an aside just to show you one thing. I think this will be helpful just to go over the stacking because it is kind of confusing sometimes. So I'll just go over it really quick before we move on. And so the part I'm talking about in particular is this update step v1. And so we have like this NP stack of this indexing, blah, 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 blah. Let me just go over what that actually looks like. So first thing is we have the data here. Oh, let me just stop this. Okay. So we have data here. We know it's like n by d, right? This is n by d. So it has like a size 5,000 by 26. And basically we know that labels here, these are a bunch of labels from 0 to k. And so basically this tells us which centroid each data point belongs to. So for example, this tells us that the 0th element of data belongs to centroid 9. So let's take, for example, centroid 1, right? If we say equals 1, we get like this Boolean mask of which points actually belong to 1. And if we take a sum here, we can see a total of 178 points belong to the centroid 1, which is like the second centroid. When we actually do this mask here, labels equals 1, we take a shape, this returns like 178 of the points that actually belong to that centroid. So we can see here that we have 178 points that are supposed to belong there, and our final data shape ends up being 178 by D. And our last step, when we do this mean, is you end up with, let me give you the shape. You basically end up with one. I realize how bad of a decision it was to make K and D the same, but I'm just going to say K and D instead of 26. But you can see that we have one array of dimension D that's left over, and this is the new centroid for that group. And so this is the average of all 178 points that belong to centroid 1. I hope that clears it up a little bit before we move on. If you have any questions, feel free to pop it in. Cool. Okay, now we're going to get into like the meat of the presentation. And so this is the first of the two parts. We're going to be talking about optimizing the assignment step. And so this is the step where for every data point, we're going to determine which centroid it belongs to. So this is what we have right now. As you guys remember, we kind of create this labels thing, and every turn we look for the closest point and assign that into the label. And this basically takes like 1 second to run, which is not great. And so what are some issues that we see here? So in the beginning of the presentation, I was talking about avoiding for loops and vectorizing code. And so what do I mean by that? Generally, when you're writing a for loop in Python, this means that things are happening sequentially. So for example, data point 0 is going to come before data point 1, et cetera, et cetera. But data point 0 and data point 1 aren't like related for the purposes of this algorithm, right? They can be dealt with individually. And so in that sense, they can be run in parallel. And so what I mean by that is you can determine which centroid is closest to 1 at the same time that you can determine which centroid is closest to 0. And the same sense, like here within this loop, you can kind of determine which, the distance between centroid 0 and 1 to like any given point at the same time. So that may not make sense, but it'll make more sense when I go to the next slide here. So we're going to be talking about this line in particular. We want to get rid of this for loop first and make sure that this comparison to centroids happens at the same time. And it's as simple as doing this. And so I'm going to explain what this code does, but essentially instead of doing this loop here, we're going to just take the difference between the point and all the centroids at the same time and then compute the norm. And so this may look a little bit confusing, but that will make sense after the next few slides. So what magic we just did there is something called broadcasting. And so broadcasting is basically how NumPy does operations with arrays of different sizes. And so in this example, you can see that we have this array A, which has like size 3, and we have this array B, which only has size 1, right? Only has one element in it. But if we add these in NumPy, we know that we'll get a result of size 3. And the question is like, how does that work? Like, why does NumPy not just add the 2 to the first element? Or why doesn't it produce an error? And this is one of the special things about NumPy. It does this thing called broadcasting where it pretends that this B is like the same shape as A. And so it pretends to stretch the array to the same size and repeats the elements inside. Once it does this repetition, then you can successfully add this element-wise, right? Like 2 plus 1, and then 2 plus 2, and then 2 plus 3 to get this final array. So let's look at a more detailed example to kind of explain this more intuitively. And so we'll start by these like broadcasting rules. So in this example here, we have this array A, which is like 4 by 3. So it's like a matrix here. And then we have this vector B, which is only of size 3. So it's like a row vector of size 3. And our final result is 4 by 3. And the question is why and how does this work exactly? So here I have the shape of A, which is 4 by 3, and I also have the shape of B, which is just 3. So the first thing that broadcast does is it right lines the shapes here. So we're going to basically line up the shapes along the right, exactly as the name implies. And so we have 4 by 3 and 3 still. The second thing we're going to do is we're going to left pad the shorter shapes with a bunch of 1s. And so here, for example, we know B is the shorter, obviously it has fewer dimensions. And so we're going to left pad this with a 1. And so now A and B kind of pretend to have the same number of like axes. The next thing is that we have to check, okay, so do the corresponding dimensions either match or have 1s? And so here we can see that, all right, these two dimensions are corresponding and they match, which is good. And these two dimensions are corresponding, whereas a 4 and a 1, and that's totally fine. It either has to match or have a 1. And you'll see in the next step why this 1 is important. And then the last thing we do is we stretch these 1 dimensions to match the dimensions of the larger arrays. And so in this example here, B used to pretend to have a 1 here, and now it stretches to pretend to have a 4. So now these two things are the same shape, and we can actually add them together element-wise to produce this final result here. Before I move on, kind of questions about those 3 steps, or we're going to do a few more examples. It'll make a little bit more sense after those, but any intermediate questions? Slido. Nope. Okay. Let's look at another example. And this example is one where broadcasting fails, where we can't actually add the two shapes together. So we go through all of our regular steps, right? We have this 4, we right align the 4 and the 3. We left pad this one with 1 because this is has fewer axes. And then we have to ensure the corresponding dimensions match or have 1s. And we can see that here, this 3 doesn't match the 4, which is why broadcasting fails here. And so that's why it's important that, see like the 3 matches in the second dimension here, but it doesn't match in the second dimension here, which is why it fails. One more example, and hopefully it'll clarify it a little bit more. And here's a second, slightly more interesting example here. We have this column vector A, like a 4x1 array. And so this is like a column vector of size 4. We have this row vector of size 3, which is B. And so we want to broadcast these two together to kind of produce our 4x3 result in the end. And so you can see here I have the two shapes. Once again, A has shape 4x1, it's a column vector. And B is a row vector of size 3. We go through all the normal steps. So for step 1 is right align the shapes. And so now they're right aligned. Step 2, we left pad the shorter one with 1s. And so B once again was a shorter one. So we left pad it with 1s. Step 3 is we have to ensure that all these corresponding dimensions either match or have 1s. And so here, for example, we have 1 and 3, totally fine. And 4 and 1 are totally fine as well. The next thing is, this is the more interesting part of this example. When we actually stretch these arrays, both of these arrays are going to be stretched to match each other. So in particular, this array, this column vector A is going to now pretend to be a 4x3 matrix by stretching in the, adding more columns essentially. And this 3-dimensional row vector B is going to pretend to have more rows. And so it's going to basically pretend to be another 4x3 vector. And now we can actually add these together to produce our 4x3 result. So that was a lot, and that was kind of fast. And we'll kind of illustrate it with our Kmeans example about why this actually works. But any question? Okay, nice question. So good question. No. So in general, okay, yeah. So the broadcasting rules for matrix multiplication are slightly more complicated, right? Because for element-wise operations like addition, subtraction, multiplication, division, these happen like element-wise in our arrays. And so they just have to end up having the same shape. Whereas for matrix multiplication, you kind of need the inner dimensions to match, right? And the outer dimensions cannot match. So if you actually go to the link I have here, this link will take you to the NumPy page for broadcasting. And obviously, if you have these slides, you'll have that link. And those will actually go through some matrix multiplication example. Next question. Does broadcasting copy data at all? Good question. So when we're actually doing this stretching operation, no data is copied. NumPy is just pretending that this vector is larger than it actually is. And same thing here. So there's no copies made of A or B. But the final result obviously is a brand new array, right? It's not sharing any memory with the original. It's a whole complete 4x3. Yep. The UW Plaza subway?
Yeah, not the Plaza subway. And they said that they want to know if you ordered it to that one somewhere else, because apparently they did not receive it.
I literally paid for it. Okay, hold on, let me. All right, don't worry, food is coming, they found it. Yeah, you guys have a reason to stay now. Okay, so does that answer your question about if broadcasting copies data? I just send another question if it didn't answer your question. It's totally cool. So does the right alignment happen automatically, or do you have to program that? Good question. It happens automatically. And so the steps I showed you are basically what NumPy does under the hood to actually add these two arrays together. So in particular, here we have these arrays of different shapes, and we're are trying to add them in the code. And I'm just basically illustrating what happens in the backend to actually make this happen. And we'll see that in the Kmeans example, like this does actually happen. So you don't actually have to program that. This is just like an intuitive way to understand what's going on. No more questions. Cool. Okay, so what is actually going on here? So we can explain what we actually did now in this code. So we know that the point here is a vector of dimension d. So for example, once again, our smart for example, height and width or whatever it may be. The centroids is like a matrix by fk by d. So we have k different centroids, all of dimension d. So for example, 3 by 2 in our original explanation. We can go through the steps of actually broadcasting these, right? We can kind of right align both of these dimensions. So now these d's line up. We can pad the left with these ones, and then we can pretend that points is actually k different points, right? So now basically what we did was we took this one point and we like replicated it along like the first axis to kind of pretend it's the same shape as centroids. So now when we take this like subtraction, we now have like a matrix of, is that in the next slide? There we go. Yeah. So now when we do point minus centroids, we have like a k by 3 array where each row of this array is the difference between the point and the centroid. So for example, the 0th row would be the point minus the 0th centroid. The first row would be the point minus the first centroid, et cetera, et cetera. Then when we call np.lineal just norm, axis equals 1, basically when we specify this axis, we're saying, okay, this is the axis we want the reduction to happen over. And so more specifically, we're treating this k by 3 array, k by d array, as like k different d-dimensional arrays, and then returning like the k different distances. And so don't worry, I'll give you guys a chance to play with this code to see what that means exactly. But on a high level, does that kind of make sense? We're doing the subtraction simultaneously. We're taking the distances simultaneously. So now we have all the distances from one point to all the centroids all at the same time, like vectorized, as opposed to one loop at a time. Maybe Q&A. Oh, nope, go back. Yeah, if that didn't make sense, you'll get a chance to play with it a little bit more, and I'll come around and we can kind of go through some more examples if you guys would like. And so now we get this like huge speed up, right? Like before it took like a second, which is 1,000 milliseconds, and now it's like 72.6 milliseconds just by vectorizing this one operation, because we don't have to do this for loop. And so that's like a 14x improvement, right? Just by vectorizing this one small operation. And so now the question is, can we take this like one step further, right? Okay, so now we like parallelize this idea of a single point minus all the centroids. And so now we want to take this further. Like this outer loop here is totally not necessary, right? Like these points don't depend on each other. We could probably find the difference between all the points and all the centroids at the same time. And so this is when it gets a little bit more spicy, when we have a little bit more, some more complicated broadcasting tricks. And so this code changed a lot. What exactly happened here? And so let me explain. Do I have slides? No. Actually. So the first thing that's going on here is this is probably the hardest step of our new algorithm, right? It's this difference between all of data and all of centroids. And so what's going on here? What is this like fancy indexing? So basically NumPy, if you index with none, it adds a new axis for you. And this is necessary here for us to do the proper broadcasting. So in particular, you can see that data is n by d. I wish this thing wouldn't pop up when I did this, but whatever. It's n by d, and centroids is k by d. Let me keep my mouse still. So as you can see, this would fail the broadcasting rules, right? Like the k and the n don't match. And we're also not doing what we want to do. We want to take a difference between every data point and every centroid. So by doing this, like this colon and the none, this colon indicates we want to select everything in that dimension. And the none indicates that we want to add a new dimension. So that way it becomes like n by 1 by d. So basically this is equivalent to, okay, I'll open the collab and we can show you a little bit later, but basically we're inserting a 1 between the n and the d. And same thing with centroids here. We're inserting a 1 at the very beginning. And actually this 1 is not necessary by broadcasting rules, but I did it anyway to be a little bit more explicit. And so now we have this data with these shapes, n by 1 by d and 1 by k by d, and these will broadcast together. So basically NumPy will pretend that data is replicated k different times, once for each centroid. And it'll pretend that centroids is replicated n different times, once for each data point. So when we do the subtraction, we get this huge array, this n by k by d array, where each, or basically where each of these d-dimensional arrays is the difference between one of the centroids and one of the data points. And so yeah, we'll open up Colab right after this and you guys can explore what that idea means. But basically, essentially what we did is we parallelized taking the difference between every centroid and every data point. And so we have all these differences stored in this huge matrix, this huge array at the very start. The next step is to get the distances between all the data points and all the centroids. And we do this via the norm, and this time axis equals 2. And the reason we use 2 is because we know that this d dimension is where we want to like compute the norm over. And so we basically contract this dimension using this norm. And now we have all the distances between every single data point and every single centroid. And our final step is going to be finding the closest data point to every single centroid. And so we know we have all these distances in this big matrix, and we want the closest distance over the k dimension. And so here we're doing an argmin of these distances over this final axis here. And we now have the closest centroid, like the index of the closest centroid for every data point. Is there a next slide? Okay, cool. So that was a kind of a lot to digest because we just did like 2 steps of broadcasting all in one. We're going to go back to the notebook and we're going to go to like the second cell, and you guys can kind of take a look at what's going on there. I would suggest you like kind of pull out that code, make it like smaller, like use arrays of like size like 5 by 2 by 3 or whatever it may be, and like actually see what these differences look like and try to understand what's going on here. And the key thing is to remember is I would also like play with this indexing to see what adding different indices does, and like if you put the none somewhere else, what goes on, and like why this actually works. And the cool thing is like here, now we got like almost a 5x speed up, like a 4x speed up by like completely parallelizing this operation. And so I'll leave you guys to that Colab notebook again. And in the second cell, we have the code I just showed here. Just play with it a little bit. I would suggest like making smaller arrays, like the 5,000 by 26 by 26 is not great. 5 by 2 by 3 is what I'd recommend, and just see what the differences look like. And we'll do this for another like 5 minutes, and then we'll come back. Generally, broadcasting is like the number one tool to actually without the alternative to broadcasting is manually replicated. So like yeah, check out the notebook. You can like run these. Yeah. Good question. Do you know what? I'm actually just going to Google this right now because I do not know. Yeah, hold on. Yeah, actually, it sounds like you're totally right. So it does run this like 10 times. So it does 10 times and does like the best 5 loops. And then you notice that you get like a standard deviation and like a mean and a standard deviation. So it calculates the mean and standard deviation out of these best 5. So I think you're totally right based on my quick scroll of the time it module. All right, for the sake of time, I'm going to continue on with some of these other things, but obviously these notebooks are available after, and I gave you my email or Discord, and like we can obviously like chat about these things after the main presentation and also after this workshop altogether. But we'll just get through some more content for now. So the next couple of optimizations are kind of minor. They're not going to be as huge as this big difference we made. Like we went from 1 second to 18 milliseconds. It's pretty awesome. The next few optimizations are super small. And they're not so much NumPy, more so like math and other things like that. So the first thing we're going to do is we're going to improve this norm here. So NumPy linealgebra.norm is actually kind of a, it's a little more heavy duty than what we actually need. So would you guys agree that the norm function is equivalent to doing this here? So basically, I have norm here before, and instead if we take the square and then sum it and then square root, like that's a norm. You guys would agree, right? Like a Euclidean norm. Okay, I hope you guys agree it's the same code, should be. And the question is like, do we really need that square root there? Because if you think about the square root, it's like a monotonic function, right? It's not going to change the relative distances. And so for example, like if you have like 3 different distances and you take the square root of all these distances, the closest one in the original versus the closest one in the resultant is not going to be any different. Sorry, not the closest, I mean the smallest distance versus the before and after the square root. So we can actually get rid of that altogether. And so here we just got rid of the square root and we got like a tiny improvement here. And so this is actually kind of misleading. This improvement doesn't come purely from removing that square root. Square root is actually a very fast function and our arrays are not that big to make a huge difference here. A big reason is that NumPy lineage norm has like a lot of boilerplate because it deals with all sorts of norms. It can be like, norms for matrices and vectors. It has to decide, which order norm, and then there's different algorithms based on different norms that you use. And so all that cruft is taken away when you kind of implement it directly. But there is like an underlying lesson here as well, right? Every time you call a NumPy function, so I told you before that a lot of these operations like reshapes, transposes, strides, don't copy memory. But a lot of these computations must copy memory, right? Like you can't have a square root share the same memory as the original squared value. And so every single time you do one of these operations, you're creating a brand new allocation in a brand new array. And if you create an allocation, that's like a lot of time that's spent making this array and populating this array. So by doing fewer operations in NumPy, you can actually like kind of reduce these allocations more generally. So this is something very specific to NumPy. If you kind of think of other frameworks, if you think of like machine learning frameworks like TensorFlow or something like that, these are actually like kind of compiled using a DSL. And so, I'm sorry, TensorFlow is a DSL that allows you to compile this like graph of computations. And there, this is less of a problem, right? They can see that, oh, okay, we're doing this square and we're doing this like square root right after. We can kind of use the same block of memory and just replace values. But NumPy can't be that clever. Each operation has to run one at a time, which is why it has to actually do this new allocation here. So now that we made this small difference, okay, we have a small improvement. That's not really a real improvement, but it happened, so we'll take it. The next thing we can do is something called einsum. And so now this code I'm going to claim is directly equivalent to this one here. And so we're saying that we're taking 2 arrays of dimension nkd, which are these like difference arrays, and reducing them into nk. And we see that we get like a 2x speed up from doing this. And so what is this like mystical thing called einsum? And so basically einsum is like a very compact way to express products and sums, right? Essentially here, by taking a square, you're thinking of a product of diff with itself, right? Which is exactly what we're representing here, diff with itself. And then we want to do a product and then a sum. And so basically einsum can represent that in a very compact way. Basically, you can have einsums that are very complex with more than 2 arguments, and you can avoid the problem I was talking about before. You don't need to create intermediate arrays. You can kind of improve the readability of complex operations. you've probably seen NumPy code where you have a bunch of transposes, a bunch of matrix multiplications. You have no idea what's really going on, what the output shape is. But here it's like pretty clear what the input shapes and the output shapes are. And so it's really nice for readability, at least in my opinion. And the really cool thing about EinsSum is now, since you give it all the information up front, not doing separate operations, you can actually optimize the order of these operations. And so if you have a bunch of different arrays, you can do like the optimal order of matrix multiplications to use the least memory, for example, or use the have the fastest speed. So I'm not actually going to go over EinsSum in detail, but I'll leave these two links here, and these articles do an awesome job of explaining how it works. Honestly, starting to use EinsSum in my own code like kind of changed my life. The performance difference really didn't matter for me, like whatever, like matrix multiplication is the same speed. But just being able to see the dimensions, what's the input and what's the output, just made the code so much more clear and it's like so much easier to express ideas. And so I highly recommend reading these two articles and trying to use it if you can. That's the end of the assignment step. And if we don't have any questions, we can move to the update step, which is very different from the assignment step, I must say. Questions? Cool. So now we'll update the, optimize the update step. So in the assignment step, a lot of our work was kind of focused on vectorization, right? We want to get rid of this loop and just do everything at once. And so that's what we did. And we ended up getting like a huge speed up, right? It was like a 14 times 4x speed up. Like it was like, you know, from like a second to like 9 milliseconds. It was crazy. The update step is going to be a little bit harder to vectorize, right? We don't have some obvious way of doing everything at once. And so we're going to have to use some mathematical tricks to actually get there. And there's not going to be too complex, but you should try to get used to thinking about these operations in different ways than just straight up coding it in the naive way that you think of. So this is our original like update step, right? I kind of explained what was going on earlier in the collab. We kind of take the average of all the data points within each cluster, and we stack them all together to get our like new centroids. I know this code is looking at it now during the presentation. It's not the clearest code. I could have written this differently, but it is what it is, and it happens. And so this code is actually pretty fast already. It only takes a millisecond to run, which is great. And so now we have the task of like improving this. So kind of looking at it immediately, like what problem spots do we see, right? The first thing is that we have this for loop here. And I said before that for loops are not great. We don't know if this is really a problem or not, that we should really benchmark and figure it out, but getting rid of the for loop is probably a good idea. The other thing is time complexity, right? This is doing a lot of extra work. If you think about it, every time we do like labels equals I and create that Boolean matrix, that's like linear work with respect to like the number of data points. And then once we kind of index data with that, that's like another like n times d points, because we have to actually move, we have to do that linear indexing, and then we have to move arrays of size d and like up to however many different elements there are for that centroid. We calculate this mean, and it's still n by d because we take this like, you know, this group for each centroid, and we take an average. I'm going to do this for every single element in the every single centroid that we have. And so the total work is like n times d times k. And we'll see that we can actually do much better than this. If you guys are not familiar with big O notation, that's out of the scope of this presentation, but I would hope that you guys have some familiarity with like from like first year courses, but if not, we can chat afterward. So before kind of revealing how we're going to do this in the future, let's take a step back and kind of build the thing up from bottom up. So labels actually contains, we know that labels is like basically a vector or an array that contains a centroid index for each data point, right? So it's n has length n and has an index in each position. The next thing we need to make this a little bit faster is a matrix where each data point, like the row, is one hot. And I'm going to actually explain what that means right now. So we have labels here, which basically tells us which centroid that each data point belongs to. So for example, this first data point belongs to centroid 1, second data point belongs to centroid 0, et cetera, et cetera. The tool we're going to use to help us construct this matrix is the identity matrix, actually. So here we have a 3x3 identity matrix, the same size as the number of centroids. I'm sure you guys are familiar with an identity matrix. It has a 1, no, the first row has a 1, the first position, second row has a 1, the second position, et cetera, et cetera, et cetera. And so basically, we're going to use something called advanced indexing in Python to actually generate this matrix here. And I'm going to go step by step of what this matrix actually represents. So advanced indexing basically pulls out the rows from this matrix that correspond to the indices in this matrix. So as you can see, we're indexing with these labels here. So in particular, this first element, we're looking for the first row. So this first row here, and that becomes like the first element of our new matrix. The second element is 0. We're looking for the 0th row, and that becomes the second element of this matrix. Third one's a 2, looking for like the second or the 2th row of this identity matrix, and that becomes the index here. Again, we're looking for 2. And finally, we're looking for 1 again. So I didn't explain why we need this matrix. I just said that we want it. And this is something like, if you are familiar with like some machine learning stuff, you may have used something like this before. But does this kind of make sense about what this matrix is and how we constructed it? Any questions about how we made it? Let me go through this example again. No? Okay, cool. So, I need some water, hold on. So you know that we need to take an average of these data points by each group, right? And so one step behind that is taking the sum of the points within each group. And so basically, I'm going to demonstrate here that this matrix multiplication actually gives you a sum by each cluster. And so just for the initial assumption, pretend that we have 5 different data points. They're all of dimension 2, just like our smartphone example. And we have k equals 3 again. So just like our smartphone example, 3 different sizes. We have our one-hot matrix here, which is the same as what we just generated here, except we're taking a transpose, and so it's like a transposed array. This @ symbol is matrix multiplication. If you have used NumPy before, you have maybe seen this. And finally, I'm claiming that this matrix here, each row is the sum of all the vectors within that group for that centroid. And so let's actually take this step by step. Yeah, I'm sure all of you are familiar with matrix multiplication, but it's super helpful to have colorful boxes whenever you're doing any kind of explanation. So as you know, for a matrix multiplication, you kind of take this row on this column and you're doing a multiplication, right? And you notice this one-hot matrix is just 0s and 1s. And so when we actually do this dot product between this vector and this vector here, we're just basically pulling out this, this element 8, right? And that's exactly what we want, because we know that, let me rewind one step. So the first thing we want is the sum of all the vectors that belong to centroid 0. If we look at labels, the only vector that belongs to centroid 0, the only data point, is the second data point here. And so when we do this dot product, we're only pulling out the first dimension of the second data point. And same thing here. Now we're doing this dot product. We're pulling out only the second element of all this data, because we know only the second element belongs to the 0th centroid. If we move on to the first centroid, we know that from labels, the first and the last data points are the ones that belong to this centroid, right? So basically here, we want the sum of the first and the last elements. And so here, when we do this matrix multiplication, we see we only have 1s in the first and the last position. We pull out the first and the last numbers of data, and we do that sum, and that gives us 17. Same thing here, first and last for the second dimension, and we pull out the 3. Does that kind of make sense? Do you guys understand why doing this matrix multiplication here gives us a sum by each centroid? I can go over that again if anyone wants to pop it into the Q&A. I'd be happy to go over it again if you guys want me to clarify. Like, we have time, I can rewind. Cool, okay, I'm glad this colorful box has helped. Okay, so now we have like the sum of all the points by each centroid, right? And now the next question is, okay, we have a sum, but we really wanted the average, right? So we need a count of the number of elements within each group. So how are we gonna actually get that out? The first thing we can do is we can take a sum across a 0th dimension, right? We have like this matrix of 0s and 1s. Once we do the sum, we'll end up with this array here. You know, we have 1 element for centroid 0, 2 elements for centroid 1, 2 elements for centroid 2. But really, this takes like n times k work, right? We have this like huge n by k matrix that we're taking a sum of. So the total work will actually be larger than what we need. And so we're going to use a function called NumPy like .bin count. And so this really literally does a count by bins, right? And so I have a label of integers here. And so we know that there will be like k different bins because we know there'll be k different centroids. And we literally count. So it'll go like the first element's a 1. And so, it'll count 1 for 1. It'll be like 1 for 0, 1 for 2. Now there's 2 for 2, and now there's 2 for 1. And so we essentially like construct this like very quickly. And the time complexity ends up being n plus k, right? Because we iterate through this label array once, and we allocate this final result array once. And again, this is in the code that you can play with later, but this function is actually super duper fast. And to be honest, this is like a really slept on function in the NumPy library. This function is actually very flexible. You can give it weights, and you can do like weighted averages, and you can do weighted groups. It's really, really fast. I can see this like implemented very quickly, and like it can be used in a lot of applications. Like honestly, like adding this to your NumPy vocabulary can help you do some crazy things very quickly. And so now we're going to put all the things that we just talked about together, right? So the first thing is we're creating this like one hot array, which I described before, this array of 0s and 1s. The next thing we're going to do is we're going to do this like matrix multiplication I described to get the sums by each cluster. And finally, we're going to get like these cluster counts so we can eventually like see what to normalize by using this like bin count before. And I'm using the special indexing here because we need to have the right shapes to have broadcasting happen correctly. And you can explore that in the notebook afterward. And finally, we're dividing the cluster sums by the cluster counts. And so basically we have the average point for each cluster. And ta-da, that's our like new update step. And now this is like fully vectorized, but you'll see this is not much faster than what we had before. Before it was like 1.2 milliseconds-ish, and now it's like just 1 millisecond. You know, before when we vectorized this loop, we got a huge improvement, but here we don't get such a big improvement, right? And the reason is as follows: like the time complexity still like NDK. Like even though we have some more parallelization, it's really not enough. Like the previous solution had enough parallelization in terms of how the Boolean mass was computed and the mean was computed. And so we get a slight improvement, but it's still not so huge. And the overall asymptotic complexity is about the same as what we had before. So yeah, I just went over a bunch of stuff, which included like the one-hot matrix, getting the sums, getting the counts, and then getting the average. Any question about any of those 4 steps? We have time. I'd be happy to kind of go through any of those again. No, all make sense? Cool. Okay, cool. So like what now? Like how do we improve this? We already vectorized, which is like the main tool that we were taking advantage of in the previous few slides, but like we're stuck. And so the one insight you have to have is like, okay, now with this one-hot matrix only has n non-zero values. Despite the fact that it's an n by k matrix, we only have n non-zero values like by construction, by the way we created it. But the problem is our matrix multiplication uses n by k values, right? It doesn't ignore the zeros. It uses all these like kind of these useless multiplications with the zeros. And so basically we want a way to do this matrix multiplication, but only on the non-zero values. And that is to say like only the, the n different values that are in our matrix as opposed to the n times k. And this is like where sparse matrices can be applied and are super useful here. So what is a sparse matrix? So sparse matrices, so SciPy is kind of converting their terminology. They're called sparse arrays now, but that doesn't matter. Sparse matrices kind of store the non-zero values and the position where these non-zero values are. So normally in a dense matrix, we'd have like all the values in their actual positions. Here you can kind of think of like a dictionary where a particular position will either give you the actual value or it'll return 0 if that value doesn't exist. And so if you imagine if you have a sparse array, that is an array that has very few non-zero values, this is a lot more efficiently stored in memory, right? Like you don't need an n by k, you just need n different values here. So I won't go into detail about every single kind of sparse matrix in SciPy. They're all optimized for very different reasons. They all store the information in a very different way, even though they all have the same fundamental property of storing kind of only the non-zero values. They're all very different. We're just going to care about 2 particular kinds of sparse matrices. And these are CSR and CSC. So compressed sparse row and compressed sparse, not row again, this should be called copy and paste mistake. Anyway, so I'm not going to explain precisely how these stores. This presentation is really focused on using these things as opposed to kind of like understanding how they are under the hood. But if you want like a high level explanation, CSR is more space efficient when there's fewer rows, and CSC is more space efficient when there are fewer columns. And this is in terms of storage alone. In terms of like actual performance, it's really hard to tell like what's going to be better for your application. So I would honestly try both. Like these 2 are the main high performance ones in the sense that they do computations really quickly. So just really try both and benchmark and see what works better for your application. So how are we going to use this in our application here? So we're literally going to replace our one-hot matrix with a sparse matrix instead. And so here's how that's going to work. So the constructor for the CSC matrix, so I did the work for you guys. CSC is faster in this case. So the constructor basically takes all the non-zero values. It takes the row indices where these values live and the column indices where these values live. So in particular for a one-hot matrix, and so here this is one-hot T, there's like a transpose of it, like it's not, it's the transpose of our original one-hot matrix. We know all the non-zero values are just ones, and we know there are exactly n of these ones, right? Like by construction, we know there's n because each data point only belongs to one centroid. The next thing is the row indices, and that's going to be the labels, right? Like which row is the one going to belonging? Well, it depends on the label, right? But depends on which centroid it goes to. And so the indices are these centroids. These column indices are basically going to be like 1 through n, right? We want one value per column. And so one value per column. And so we're going to have an A range, which basically gives us 0 all the way to n minus 1. And so the final shape of this array is k by n, which is the same as our previous one-hot transpose array. I know verbally it's not so compelling to explain these things. because it's like hard to understand code when I speak out loud. But when you guys go back to the notebook, you guys can play around with this. This is like the fourth block in the notebook that you can play with. Again, we still need the group counts in order to do our average, but now we do the exact same thing we did before, except with these sparse matrices. The great thing about SciPy sparse matrices is they follow the same API as the NumPy ones, as the NumPy arrays. And so you can use most of the same operations, and like it'll basically call a different implementation that's designed for these sparse matrices. So in particular here, we're doing this matrix multiplication with this one hot matrix, and we're dividing by group counts. So doing the exact same thing. Sum by cluster, divide by counts gives you the mean point per cluster, which is a new centroid here. And I'm not going to prove this here, but if you actually go to the blog post I linked, we actually explain why the time complexity happens the way it does. But instead of being n times d times k, this is d times n plus k, which is like an improvement in the asymptotic properties. And so here our like time is cut in half for the particular specifications of our problem. And we're at like 500 microseconds as opposed to 1 millisecond, which is pretty great. I said a lot of words. Any questions about this slide here? Q&A. Oh, Q&A. Yes, we could. Yeah, we could do that. Good question. Let me just go through like the rest, and then after that, we'll do the Einstein demo. Person who asked this question, if you have like a particular problem in mind, that would be helpful. Or I can just go to one of the blog posts, actually, to be honest. Okay, let me just wrap up, and then we can kind of get to that demo. So kind of a review of what we did today. The first thing is we looked at broadcasting as a tool to vectorize our NumPy loops, right? Like without broadcasting, it would have been super annoying to actually do these things in parallel. We would have had to manually either copy these arrays, which like takes time and space, or we would have had to use, I mean, apart from copying the arrays to like make them match sizes, I don't even know what you could do, right? Like broadcasting is really a powerful tool to help us do these things in parallel. When we moved to our update step, we found that we can't always just rely on broadcasting, right? Sometimes we have to use other mathematical tricks to help us either reduce the work through sparse matrices or just help vectorize, right? Through the fact that we use a matrix multiplication instead of a for loop of averages. And the final thing is that, in our final step, CS 135 was actually useful, right? Like improving the asymptotic properties is like, has the biggest impact, and using like kind of utilities like sparse matrices helps us do so. And so that's something you should always kind of keep in mind. And I will add that sometimes in NumPy, the reverse can be true, right? Like sometimes the clever asymptotic algorithm is not necessarily the fastest in practice, especially when you have like a small array. One particular example is like instead of doing binary search in a NumPy array, if you literally just brute force compare all of them in a vectorized fashion, the Python binary search is not going to be as fast as a C implemented brute force search. Anyway, that's an aside, but that's on like smaller problems. Okay. So before I get to the final questions, actually, these are some resources for further learning. And so the first one, this is like easily like one of my favorite talks about NumPy. So it talks about advanced NumPy usage. And this goes over some of the stuff I covered today, as well as like other things like, for example, working with strides, working with the underlying memory. To be honest, that's the most helpful part of this talk, is like the underlying memory model for Python. The second link is like kind of complementary to this workshop. So kind of a lot of these like kind of functions I implemented were for this like kind of blog post I wrote about implementing Kmeans really fast. And so there's some stuff in this presentation that wasn't covered in the blog post, but the blog post has a lot more detail on the things that it does cover. And also is more extensive. So if you're curious about any of these things or want more justification for why we did these things, I would check out this blog post here. And the final thing is that people are really interested is stride tricks. And so this is something I really love and something I learned about recently. And actually it's something that's kind of introduced in a more recent NumPy version as well. But this is basically more advanced ways to interpret the data. So I mentioned before that a NumPy array is just a block of memory that's interpreted in different ways. And so there are many tricks you can use from the library to like, prevent copying the data and still manipulate it in interesting ways. So one example is like, if you want to do a sliding window on a NumPy array, normally you'd think of doing a loop and changing the indices. But there's actually functions within NumPy like that allow you to look at it in a strided view without actually changing the underlying memory at all. You just have like an interesting view of the data. I think this is like super advanced, and honestly, like I'm awful with stride stuff. I'm just starting to learn, but if you're interested, like it's very cool. And yeah, thank you for coming. I enjoy giving this talk, especially being in person. It's great to be back. If you guys want food, please fill out this form. Like even if you don't have feedback, just say like no feedback. It's totally fine, but you're gonna have to present. We're gonna have to see your name like in the submission for this raffle link before you can go grab food. So yeah, thanks for coming. Okay, so Someone in the Q&A asked for like an InSum demo. I can actually do that right now. While you guys are filling out the form, let me just do some InSum stuff. Oh, let me, do you guys see the form? You guys have a chance to grab it? Yep. Oh, really? Hold on. Works? Cool, okay. InSum stuff. Okay, let me just actually go to those blog posts. Actually, okay, the Q&A asked for an InSum demo, so I'm going to cheat and just show the demos from the NumPy documentation. But we can, nope, these are not the demos I want. Hold on, well, it might be one of these blog posts. Oh. How do I click this? Oh. Okay, so here, like, okay, this is like a silly demo, right? But this is not going to explain how InSum works, unfortunately. We're kind of out of time to do that, but I can show you some cool applications of InSum. So here, for example, pretend you have A, which is like some 2D matrix. You can obviously taking I and J gives you back A. If you this is wrong, actually. Hold on. Ignore that one. That one is, let me scroll so you don't see it. Okay, cool. So for example, if you take like I realize now that just looking at these without actually understanding how InSum works is just completely confusing. If the person that asked me this question wants to DM me later, we can do some more, but it's not going to make sense to do this right now. Anyway, thanks everyone for coming.